Hello, and welcome to a crash course in crash reporting. But for the next 20 minutes, we're going to cover how you would build a crash reporting SDK from scratch on the Android platform. A little bit about myself. I'm Jamie. I work at Bugsnag, and I develop our Android crash reporting SDK there, which lets you measure the stability of your application in real time. So before we go into how you'd build a crash reporting SDK, let's first ask ourselves why we should even care about those crashes. So essentially, it's because users get very, very annoyed, and it's bad for your business if your app is crashing. Something like 60% of users, if they experience a crash, they'll just straight up uninstall your app from their phone, and you won't get a second chance. So it can be very important to be notified about these events as quickly as possible. If you don't have something like this, then it's quite possible you'll find out like a week or two down the line when the bad reviews start coming in on Google Play Store, and I'm sure everyone's seen something a bit like this before. So crash reporting SDKs basically work like they're a library which you'd integrate into your app. Typically, they'll hook into the platform's error reporting APIs and automatically capture errors, then basically send a report to an API. And when that's done in aggregate across all of your devices, you can sort of get a feel for how stable your application is and how crashy it is, and you can measure that in real time. So Bugsnag is one example of a crash reporting solution. So we have SDKs on 50+ platforms, including Android. We've also got iOS, React Native, Unity, etc. And we offer quite a few integrations with commonly used tools, so you can get pinged on Slack when an error spikes, for instance, or PagerDuty. So in terms of the information you get back from an individual error, this screen is sort of the information that you'd want. You get a stat trace showing you what happened in the lead up to an error, and various metadata about the device or application on which the error occurred. And at a more aggregate level, you can sort of measure like how many sessions of the app were crash-free and how many weren't. So if it goes down, your users are having a bad time. And if it's at 99.99%, you're probably okay to focus on developing new features. So very broadly, error reporting SDKs work by firstly capturing a source of errors. So that could be an uncaught exception. It could be something like an ANR, where you've blocked the main thread for about 5 seconds. Then once you've got that error source, you want to generate a report from it. So you want to grab stuff like the stat trace, so you can figure out where the offending piece of code is. You also want to grab some metadata. For instance, you might be encountering a crash on a certain device manufacturer, like a Samsung device. It's quite useful to have that information to debug the trickier ones. Then finally, you want your SDK to deliver reports to a backend. You typically do that by serializing some JSON and making a HTTP request. So that all sounds pretty simple, but the devil's a little bit in the details. So let's dive into that a bit more and start out with capturing errors. So on Android, for a JVM crash reporting SDK, you'd want to implement an UncaughtExceptionHandler, which looks a little like this. So we have quite a simple program here, which just creates a simple exception handler class, which implements the UncaughtExceptionHandler. And within that UncaughtExceptionHandler interface, there's just one method, an UncaughtException, and this is basically invoked whenever there's an uncaught exception in the program's execution. So if we wanted to set a handler for whenever that occurred, we would just call this threads.setDefault UncaughtExceptionHandler. and then our handler is what will be invoked. So the next step we'd want to take is to grab a stat trace in our UncaughtExceptionHandler. And then we'd probably want to do something useful with that rather than just like log it out, which is the default action. So stat traces can be useful, but we don't want to just deliver a stat trace. We need some extra information. So for instance, like metadata about what the device was, what the API level was, can really be useful in debugging issues. So we'll just encapsulate that into a report class. So we have our UncaughtExceptionHandler, which grabs a stat trace from the exception, and it'll just now create a report instead. So that will allow us to add additional metadata at a later time. You also need to deliver that report. We'll just create a delivery interface, which is an abstraction. So in a real crash reporting SDK, this would like make a HTTP request or cache the reports on disk if needed. And just to demonstrate that we could add additional metadata here onto our report, we've also chosen to capture the thread traces by calling thread.get stat traces. So that can be really useful to debug concurrency issues or bugs caused by concurrency. So we've now captured pretty much most of the useful information we'd want in our crash reporting SDK. So the next step is to deliver it. So with an error report, you typically want to serialize it as JSON and send it to REST API. You want to send it as quickly as possible in a crash reporting SDK, because if about 60% of your users are going to install it as their first, as soon as there's a crash in your app, you want to send it as soon as humanly possible. At the same time, we're on a mobile device, so we also need to consider that there may not be a great network connection, or there may be no network connection if like someone's on an airplane or in a tunnel. So delivery should also cache those reports on disk if it's not possible to deliver. And this just enumerates some of the potential cases where that delivery fails. So there's no network connection, there's an uncaught exception. This is peculiar to crash reporting SDKs. So after there's an uncaught exception in your app, the process is going to terminate pretty shortly. And also the servers might be down. So it's quite useful being able to cache that report on disk and then send the report at a later date. So we've now pretty much figured out how to capture uncaught exceptions and deliver them using a HTTP client of choice. But it would be quite useful to be able to capture other errors and report on those, because we need to get some insights. So there's quite a few errors which don't propagate to an uncaught exception handler. So you might have a try catch block, which catches any throwable, like a null pointer exception. And anything within that try block won't propagate to the uncaught exception handler unless it's rethrown. You've also got some interesting ones like ANRs, so application not responding. They don't actually throw exceptions, but they still really impact the user. Because if your main thread is blocked for about 5 seconds and the user notices that, they could kill their app and you might never know about that otherwise. And there's also, finally, a few other libraries such as RxJava and Kotlin coroutines, which use some custom error handling flows. So it can be useful to hook into those and get some more information. So it sort of comes down to it. It sort of comes down to we want another method on our crash reporting SDK surface, which allows users to manually notify if an error has occurred. So let's just do that. We'll call it notify, our method. And our crash reporter will look something like this. We have a delivery field, which will deliver the created report. And we've implemented a UncaughtExceptionHandler so that we do continue to capture those exceptions which are thrown and not handled in our application. And we now add this method called notify, which looks much the same. So it takes a single parameter throwable. It creates a crash report, which grabs the stat trace and whatever other metadata we need. And then it's delivered to our HTTP endpoint. We can also factor this out because there's a bit of commonality between unhandled exceptions and handled exceptions. That is an exception which was in a catch block or something like that. We can also choose to add some additional information there. We can choose to capture whether an error terminated the process or not, or whether it didn't, because that's going to sort of affect how much time we want to investigate into a bug. If there's an uncaught exception which is crashing the app, then it's probably really important, and we should prioritize that for triage. Whereas if there's something in a try-catch block, perhaps a buggy piece of code which is known to fail on a certain API level, but is handled by some recovery code written by the developer, it doesn't matter too much, so we can get an insight into how much is happening, but we don't have to prioritize that for action. So we now have a crash reporting SDK which captures errors, delivers them, and allows users to manually notify of their own errors. So the next thing is to consider is obfuscation and minification. So a lot of apps use obfuscation. So there's several benefits to why you'd want to do that. It makes it harder to reverse engineer an app or basically skin it and clone. There's several developers who will clone an existing app and rip it off as their own. Obfuscation also tends to get bundled in with minification, which removes dead code. And although they're not necessarily the same, they tend to be performed at the same time. And a smaller app basically means your app takes longer to less time to download, and it takes up less disk space on your user's device, which makes them more likely to download it. So there's a couple of disadvantages of obfuscation when it comes to crash reporting. So if we consider a stat trace in, if we consider the following stat trace, which is in a networking library. Before obfuscation, this looks reasonably easy to understand. There's a download manager class, which downloads a file. And we can see at the top frame, something went wrong in this request interceptor class. But after obfuscation, it's a lot harder to interpret. So how do we reconcile this with a crash reporting SDK? So mapping files are basically the answer to this. Most obfuscation tools like ProGuard, R8, DexGuard will produce a mapping file, which allows you to effectively deobfuscate symbols. Although sometimes there are aggressive optimizations which can make this obfuscation a one-way trip. So for instance, if you remove file names in your ProGuard configuration, it may not be possible to get exactly the same stat trace back. So let's walk through what applying a mapping file would actually look like. So we have our obfuscated stat trace here, which is pretty incomprehensible. And we have the mapping file, which in reality would be much larger, but we've just chosen the section which corresponds to the symbols we're interested in. So the first step we'd want to take is to go through frame by frame and find the class name, which in our example is com.a.a.c.a. And we need to find the one which that corresponds to in the mapping file, which in this case is request interceptor. And as we know that's the unique class name, we can simply apply it to the frame. So we now have a package name and a file name for our first frame. And we can take it further. We can go down and have a look at all the methods names and line numbers for this particular entry in the mapping file. And we can substitute them in for a frame until we have a complete frame. And then it's just a case of decoding all the rest until we have our deobfuscated stat trace. And this is coincidentally why every crash reporting SDK has a Gradle plugin. You want to perform this deobfuscation on the back end because you don't really want to ship the mapping file with your application because it can be quite big, and it also escapes the point of obfuscating it in the first place. If there's a mapping file shipped with your application, anyone trying to reverse engineer your app can do it pretty easily. So most Gradle plugins will hook into the build lifecycle and automatically upload these mapping files whenever you make a build, whether it be on your local machine or on CI. So I just want to cover a little bit about what sorts of metadata can be useful to capture when you're writing a crash reporting SDK. Because it's often the case that a stat trace is not enough to debug an issue, and getting that additional bit of metadata can be really, really helpful. So there's a couple of things that you can always capture, and crash reporting SDKs often do capture by default. So the device manufacturer, the API level, and OS level. And you can also capture some mutable values, like the screen orientation. So you can check whether a crash is happening exclusively in portrait, for instance. That may indicate that there's a layout bug that's causing a crash. And you can also capture some more interesting things as well. So for instance, if you use A/B experiments in your app, that can be added on as metadata. And then you can see if a particular A/B experiment crashes the app more and determine whether you want to ship that particular experiment. So let's have a look at our reports class and think about how we'd capture some metadata. The obvious way would be to add a metadata field. And then within our report, we can capture the common field we're creating it. So the build manufacturer, that's static. The available memory, for instance, that's a mutable value, but we can still capture that by default and it will apply to everyone. We also want to allow our end users to add that metadata. So for instance, in the A/B experiment example I mentioned before, you can't really capture that by default as an SDK, but you can allow users to add their own metadata, which can be really useful. So you can filter that on a back end, so you can segment crashes and prioritize paid customers, for instance. So you do this using something a little bit like this. So we have our notify call, which creates a report and delivers it. And essentially, we just want to add in a lambda here, which users can alter the report. And then we want to add a method which allows users to add their own metadata. So they can detect whether there's a paying customer or whether there's a particular landing screen in use in an A/B experiment. Another thing I'd like to touch on quickly is the concept of breadcrumbs. So this is something that Bugsnag will capture automatically, and it can be really, really useful for capturing the lead up to a crash. So they're tracked independently as a sort of buffer of events which happen before a crash. So for instance, if there's a connectivity change, it may be useful in finding out why a request has failed. Or there may be navigation changes in your app, that lead to some subtle, hard to discover bug. Let's just recap quickly. So crashes can be really, really frustrating for end users. And this is like one reason why crash reporting SDKs are so widely used and bring so much value. So if you want to start writing your own crash reporting SDK, you'd start out with an UncaughtExceptionHandler. So that's where the JVM escalates all uncaught exceptions. You'd then basically generate a JSON body, which could be sent into a HTTP endpoint. You could generate that from an on-caught exception or a handled exception from your own source. You also need to think about caching reports and how you'd redeliver a crash report when you regain a network connection. Finally, you want to consider stat traces. You need to upload a mapping file to deobfuscate from on the back end. And it's really, really, really important to consider what sort of metadata can make your error reports more useful. It will differ for your own app. Everyone has a different app that they develop, and you will have individual metadata to that app. So logging experiments as metadata can be very useful, and it can really save you time debugging. Thanks very much for listening to the talk, and you can find Bugsnag in the virtual expo hall.